Hi, everyone. Hello. Hi. I am going to wait for a few more people to join as it's just time. So we're going to give a few more people to come on. But hello, welcome. Welcome so much to this webinar, the second ever Witekio Octavo webinar together. It's going to be glorious, I promise you. Some great content, some great speakers. You just have to be a tiny bit more patient. So a few more can join and then we will get started. So yes, welcome, come in. If you're on StreamYard, you can say hi and you can chat, I think this way in the corner in the comments. If you're on LinkedIn, hello. If you're on YouTube, hi. Write your comments and your questions in the chats and we're going to answer them live at the end. So that's also a bonus. So if there's anything you don't understand, if there's anything that is specific to maybe one of the experts, whether it's from Octavo talking about the hardware and security side, or Witekio talking about the software security side, that you're like, I've got a project that I kind of am working on and I need to understand this, put it in, and I promise you, if they don't know the answer, we collectively will have someone who will, and we will get back to you. So yes, welcome, more people, hello, welcome to this webinar. As I said, just give me another 20 seconds and we will begin for real. Just going to check that everything is going well, and then we'll get going. Hi, everyone. My name is Georgie Ryan Casling. I am the head of partnerships and the marketing team lead for Witekio. And welcome to this amazing webinar with Octavo Systems, all about best practices for building a secure embedded system, in brackets on SIP, because it's Octavo. So in a minute, I am going to announce our lovely speakers and they can introduce themselves. But just so you know, some ground rules from me and gatekeeping and all the rest I need to do. Essentially, as I said to anyone who joined before, answer your questions and they will be answered live at the end. So please get commenting away. If there's something you want clarified or if you have something you want to talk about, then please do. And it doesn't matter which platform you're on, I will receive them. So that's it. Very quickly before we get started, obviously this is a Witekio webinar with Octavo as our partner, and Octavo will tell you all about themselves in about 20 minutes and you're going to love it. But just effectively what Witekio can do for you. Witekio is an embedded and IoT software services company. We do everything from chip to cloud. So that means from your low-level embedded development all the way up to your applications, your middleware, your lovely, sexy touchscreens, all the rest of it, to cloud connectivity, security, and beyond. I'm not going to bore you with it. You can go onto witekio.com and see for yourself. That's my pitch over. And now I'm going to pass you to our experts who are going to talk all about themselves and the agenda, which is here. So I'm not going to go through this because you're about to talk about it and you know it. You signed up for the webinar, the overviews, talking about exactly what security is, about the lifecycle processes, testing, maintenance, etc., etc. So without further ado, I'm going to hand you over to Eric from Octavo, who's going to introduce himself, followed by our speakers. And I will see you all at the end.
Thanks, Georgie. My name is Eric Welsh. I am the Chief Technical Officer and Applications and Systems Manager here at Octavo System, where we're developing heterogeneous system and package devices. Myself and my team are responsible for product development, reference designs, collateral, and technical support. Basically, all the information that you can find on our website, octavosystems.com. Chris?
Hello, I'm Chris. I am a embedded engineer at Witekio. I specialize in security and embedded development. Ed, if you want to take over.
All right, thanks, Chris. My name is Ed, engineering manager, now US spin-off team lead and senior software engineer, embedded software engineer at Witekio. And I'll be kicking things off by giving you all an overview. Me and Chris are going to give you an overview of the secure development life cycle. So when discussing best practices for security nowadays in terms of developing a product or a device, it's common to hear the phrases secure development life cycle and secure by design, often thrown around in the press. So just real quick, so secure by design is a concept that you can't add security after a development, and there's no stage in a project where you do the security. The security has to be ingrained all the way through all stages of the development process, and that involves ensuring that not only the end results, which would be a hardware or software design, for many of the viewers watching this, but also that the whole process that's used to create that end result is set up with security conscious measures in mind to ensure that you have a secure product at the end of it. So in other words, the development process is by design secure, ensures a secure result, as well as just the end results that you can take out and sell to people. And that ensures that the additions to a standard development process ensure that vulnerabilities can't creep through into the final results. So the easiest way to do that is with a development process, which is commonly termed a secure development life cycle. And that is a set of guiding design principles that you use during all stages of a standard development cycle, to add additional security conscious measures. So if we go to the next slide, Georgie. So just quickly, when we use the term secure development lifecycle, we're not talking about a specific standard or framework or certification, but there are a few examples out there that you can pick up and use the Microsoft secure development process. There's a few good books, the principles from WASP, and that'll help you if you use any of those guidelines, which are basically common to what we're going to talk about now. That'll set you up nicely if you want to get a certification from one of the sort of known security certifications that different industries use. So if we jump on one, Georgie, so what are the extra steps of a secure development lifecycle as opposed to a standard one? So this diagram here is a standard development lifecycle. This diagram, as you see it there, it could represent an entire project if you're doing waterfall, or it could be a single sprint in an agile process. So most people nowadays, most companies are using some form of iterative process. So the time span of this, as you see it on the screen, could be 2 weeks, or it could be several years, depending on how you're running your project. So on the next slide, you can see the additional security steps that make a standard development cycle into what many people consider a secure development life cycle. And at the top and bottom are activities that just go on during the entire project, and that's kind of continuous improvement focused things like training, maintaining a risk management framework that you populate with risks as you go through the project and identify them. And if something goes wrong, usually after you deploy a release, you don't just want to fix things, you want to fix the process that allowed those things to happen. So that's what the bit at the bottom represents, continual process updates. But we're going to focus briefly on the stages in the project. So let's look at the extra steps that are needed during requirements capture in a project. So let's say you've started a project, you've just captured a load of requirements, or if you're doing an agile project, this might be at the stage of having just identified the acceptance criteria for a story, for example, or you're in an early sprint, which represents the formal process of requirements capture. And straight away, you can do some security analysis on those requirements as soon as you caught them. For example, just to give you a tangible example, let's say a device has to operate out of doors in a quiet area. There's a risk of somebody just physically stealing the device. You would then identify a security requirement that the device needs to be resistant to somebody who has just complete uninterrupted access to that device to just probe and measure things and just examine it at their will. If on the other hand, it's a server that's locked away inside a server center somewhere, the severity of that risk would be much lower. So you put those risks into your risk management framework, and they're all scored based on severity, and you can use that score to prioritize them. And the first thing you can then do is to identify ways to mitigate those risks with more requirements, specifically security requirements. And the aim at this point is that you want to add sufficient requirements to cover security so that nobody later on in the project ever has to utter the phrases like, the concept of this product is fundamentally flawed in terms of security, or it requires major rework to be a viable product, to be able to sell into an industry where it needs to be secure to a certain level. And a good example of this is hardware selection. For example, if a product must run only signed firmware images, you can avoid, that allows you, identifying that early on ensures that you avoid getting too far into a project without hardware that can't do secure boots, for example. So on the hardware selection side, Eric's going to tell you a lot more about that a little bit later, specifically on the topic of SIPs, and he'll discuss some of the ways that SIPs can ensure that your platform is sufficiently locked down. For example, in the case of the physical security, if somebody's able to just get a device to play with. So on moving through the stages now, Georgie. So let's say your development is moving into the design stage, either in the project in general or in the sprint. So assuming that you are producing documentation of your design in some form during your project, what you can then do, just like for the requirements, is to analyze the design and identify security risks in the designs so far. And in practice, what that generally means is looking at the architecture diagram or any other design material you've got and picking out which parts are at greater risk. People might draw red boxes around them. It's not unknown to physically print it out and get the red marker out. And the main thing to look for people who haven't done security risk analysis on designs before, usually just look for the I/O in the system. Anywhere that interfaces with an entity that's outside of the system's control. Users are an obvious one. That's usually the main malicious actor in a system is the user, but it could also be other hosts that the device networks with, a firmware server, for example. You need to ensure that you're only downloading firmware that you want the device to download. And peripherals, if the device has say a USB host port, it's not unknown for people to develop malicious USB gadgets to plug into a system. So moving on, if based on the risks identified in the architecture design, if we move on a slide, Georgie, sorry. The initial mitigation to any risks found in the design would be to modify the design based on security concerns. And doing this formally as a separate stage to analyzing the risks in the requirements capture stage, sort of demonstrating that you've done that separately really helps to build up evidence if you need to do a security audit to get a certain certification, for example. And the risks in the risk management framework are given a severity rating. So just as a tangible example of that, if your components are exposed on a PCB and people can probe and read buses, if that's a concern, because that allows a certain level of casual attack, the severity would be high. As Eric will tell you later, if you use a SIP, which prevents people from casually probing signals between components, that would reduce the severity of that risk to a level that's only the most dedicated of attackers could possibly hope to get at those signals, and that risk would then could be considered mitigated depending on your use case. So the risks and the severity are all very much dependent on what kind of device you're developing and where it's going to be used and so on. Now, so the final security steps addition in the design stage generally is for testers who are planning tests for the project, and of course, like the other stages, they also need to add security tests. So it would be hoped that there is a strategy for testing planned out for your project. If you're worried about security, usually there's a good enough amount of process that you've got some test planning in effect. So the tests that you need to add for security are usually guided by the additional security requirements that have already been identified, and the priorities from those requirements can be used to decide which tests to focus on. So the next stage is implementation, and I'm going to hand over to Chris to carry on with the security steps for the remaining life cycle stages.
All right, yeah, so to iterate back on Ed's point with having security in mind throughout the entire design process, as a security and minded engineer, I always like to preface by saying that a system without security in mind will never be secure. So it has to be thought throughout the entire process. Very important. But utilizing design tools to mitigate security throughout your whole process, like Ed was saying before, a lot of the times the hardware that you choose will have a big influence on what security methods you will use to protect your systems, such as what do we have? Trusted platform modules. They're a lot more prevalent in modern day systems. You see them in pretty much every single PC that you use today, and a lot of embedded systems nowadays are starting to use them, as they're a great way to make sure that your system is authenticated, the firmware before it boots, protects your certificates that you may have installed for accessing, say, AWS or any kind of cloud connectivity service that you could use to store data from. And they can also ensure that the code that you're pushing is also secure. And most of the chips nowadays also use secure boot signed firmware to verify that the code in fact is yours that you're pushing, and that third parties don't have access to pushing their own custom firmware to your devices. Another thing that's good to keep in mind is minimizing hardware level access to your devices, such as JTAG and buses, as these are very easy vectors to ensure that very easy attack vectors that any kind of malicious user can come in and start reprogramming your devices if they have access to them. So what can we do in the process as well? We can use static analysis tools and verify that the code that you're running is airtight before you even push it to a device. If you're running static analysis, you'll be able to see if there's any faults or access points for on the software side of things that an attacker can potentially hit. Additionally, validating code through continuous integration and continuous deployment can also help validate this as well, to make sure that it doesn't break old code, and it's just a good process to get into the habit of doing CI/CD if you have a large-scale deployment. And another thing that I always like to think is important as well is ensuring that you have a security engineer or a security-minded engineer on your team throughout the entire process. This could either be a security champion if you have a large company such that you will have somebody who is the dedicated security person for all of your projects that you may be taking on, or even if you're a single-man engineering team, just being the person who's always keeping the security of your systems in mind. So that way, you may be the fall guy for security, but there is always somebody who is thinking of these things, while other engineers who may not be as trained in that department have somebody to go to think on their behalf for that, or also teach the team different methodologies and thought processes of securing your systems. Another major important part of keeping your system secure is validating and testing your systems as you go through. So what's a great way to test your solution? You have a few different methods. Two big ones are fuzz testing, which is testing the resilience of your system from users or itself. A great example of this is just having you slam the buttons on the device. If you have buttons on your device, do the buttons jam? Having multiple buttons on at the same time, does it cause your system to go into a failure state? Or say you take the power supply and you decide to flick it halfway through, so that way it's kind of in between and kind of not, and make sure that your power circuits can actually handle something like that and not cause either it to go A, on fire and cause a hazard, or B, maybe mess with your clock signals, so that way it can slow down, undervolt the device, overvolt the device, and give it a potential vector of attack there. So it's a great way of just general field use testing, because things in the field get abused and used. You want to make sure that it stays secure and stays in good shape throughout its whole lifetime. The other kind of testing that needs to be thought of is penetration testing. This takes an attacker or a malicious user's role in the system. Like Ed was saying before, this could be the user who has the USB port access that wants to put a bad USB gadget in there and decide to crash your system to access the firmware or dump your firmware. You want to make sure that you're able to verify that somebody doesn't have an access, somebody who could have access to your device you're able to minimize and mitigate the damage that they could do. And this could actually be required for certain certifications and compliance and standards depending on where you live or what field of device you have. So it's important to keep both of these in mind when you're designing a system and maintaining the system, which leads into maintenance of your system. So there's a few things that you should think of when running maintenance on your systems. One of them is common vulnerabilities and exposures, CVE. There's a large database of CVEs rated on their severity, and which is aggregated by how easy they are to do and how bad they are. For example, the Intel chips from, I believe, 3rd gen onward had the Spectre and Meltdown vulnerabilities. Those should be on the CVE database. They are used for engineers and system administrators to verify and double check that their systems are airtight as well, and in the future to make sure that any new vulnerabilities are addressed. So we want to perform CVE scans on our live systems, and we want to perform CVE scans against our current builds. This is actually one of the services that Witekio does offer, is a CVE scanner for your builds and for your systems. So it's also very important to subscribe to the CVE newsletter. This is going to be constantly updated whenever new vulnerabilities and exposures are put out to systems. Recently, there was one, I believe, with ESP32 where you're able to dump encrypted firmware. That one just came out. So these are all things that you should really keep in mind and always be aware of when you're developing and maintaining your systems. And also system updates. We have systems in place to update our systems regularly, so that way they are protected and everything's kept up to date, whether it be certificates, whether it be the operating system itself, the firmware. We want to keep our systems up to date and secure. So having a system in place, kind of like, for example, you update every 6 months or you update twice a year. Look at, for example, Ubuntu, they do 1804 and 1811, I believe. They do 2 major updates to their operating system on a schedule. So implementing something this into your design and maintenance workflow is a great idea, even if it's just as simple as changing a build number. It makes you and your customer feel more secure that your system is being kept up to date. Another thing to do is to secure your OTA endpoints. If your device has a vulnerability that the system update can be exploited, congratulations, you need to be aware of that. Another place to keep in mind is also where you're pushing from. If your cloud service where you're pushing your OTA updates from is also compromised, an attacker could potentially take advantage of that and push their own custom firmware to millions of devices and create, say, for example, a botnet or something like that. So protecting your endpoints from end to end is just as important as protecting your devices. And another part is also protecting users from rolling back the firmware that you've pushed and updated to the devices, as you want to make sure that any previous vulnerabilities that are patched by your new updates can't be rolled back and exploited to put on, say, custom firmware in the future. So CVE scanning and system updates are both important parts to keeping maintenance up to date. So I'm going to hand off to Eric at Octavo for his bit on hardware security and SIP. So Eric.
All right, thanks, Chris. So as Chris and Ed have discussed, security is this mindset that spans your entire design. And as we've touched on a couple of times, this includes hardware as well as software. So when we look at hardware, we need to answer those same fundamental questions that we do when designing all aspects of our security system in terms of what are we protecting and who are we protecting against. And that way we can effectively mitigate risk and utilize the available hardware tools to ensure that we have the appropriate integrity, the appropriate confidentiality, the appropriate availability of the things that we want to protect and protect against and protect from others. So we're going to dive first into a couple of hardware security aspects that you should consider when you're looking at designing your product. So basically, there are four broad categories that we want to look at when we look and try to understand the security requirements of our application. The first would be communication security. And here we're basically using tools to ensure that we can correctly transmit the data from one point to another, so ensuring an integrity of the data communication. If we're looking at potentially health data or sensitive types of data, we want to ensure the confidentiality, so we want to make sure that that communication channel cannot be intercepted or snooped. And also, if we're trying to do some type of real-time monitoring for health, in which we're actively monitoring a patient, we need to make sure that the data always arrives. We need to ensure that availability. And so there's lots of tools out there, from hardware level cryptographic accelerators to a bunch of different secure protocols that allow us to be able to implement the communication security that we need for our application. And generally, when you're going to look at security, you want to make sure that you use known good tools, known good accelerators, and known good protocols, and not invent your own. I mean, there's a lot of appeal to security through obscurity, and that is never, I mean, security through obscurity is never real security. And so you want to make sure that you're using actual hardware implementations of things, and that they've been tested and certified for what you're trying to do. So that's a little bit about communication security and some of the things that you need to consider as you're doing communication security. Next is looking at boot security. So here we're trying to make sure that we guarantee that we can trust the software that's running on our product. So really, if we think about it, there are many different protocols and many different ways that we can authenticate various stages of our boot and various pieces of our boot image and things like that. And depending on your security requirements, you might need to just authenticate a small set of your boot image. So maybe the first stage bootloader or U-boot. In some cases, you might need to validate and authenticate the entirety of your boot chain, including your file system, in order to make sure that you start from a known good state. And really, as you look at boot security, you want to always start off with a hardware-based root of trust. And that really means that the processor that you're running on supports the ability to securely store keys within the device. So you really want to have that hardware-based root of trust, so that way, as you're creating this chain of trust through authentication of your boot image, you can ensure that you can actually trust all of these pieces. Additionally, you might have some software IP that you might want to protect that sits within your images on your device. That's where things like encryption come in, and making sure that you have encrypted devices and or encrypted boot images, so that way you can protect that software IP as part of your secure boot process. Next, we have the aspects of runtime security. And basically, this is making sure that we ensure these security aspects of integrity, confidentiality, and availability among the software applications running on the processor. So most folks are familiar with the concept of escalating privilege level. So How many times have we gone to install a program on Windows and the little pop-up comes up and asks us to, can you have administrator privileges in order to be able to install the software, or in Linux using superuser in order to be able to do a lot of installation or just execute certain types of commands. And so we're pretty familiar with the concept of escalating privilege level. But when we look at security and particularly runtime security, now we have another whole vector of the ability to have both a secure and a non-secure world. So basically, instead of just two states, a non-privileged and privileged, now there are four states. You have a non-privileged, non-secure, privileged, non-secure, non-privileged, secure, and then privileged, secure states in which the processor can execute. And that allows for the processor to be able to do isolation and make sure that you can retain that confidentiality or the integrity of the different applications that are running on the processor. And so depending on what your application requirements are, you may need to utilize some of these secure frameworks in order to, or security frameworks in order to be able to operate in these different secure and privilege levels. And from a hardware point of view, those a lot of that primarily gets supported through some of the ARM trust zone extensions that exist within the ARM processor families. But there are a lot of other security extensions that exist within other processor families. And so it just depends on the processor families that you're choosing in terms of what is supportable in terms of your runtime security. So when we talk about communication security, boot security, and runtime security, those are primarily processor or SoC level areas where we want to focus on security. They're really just, if you look at the particular SoC or processor that you want to use for your application, that's where you're going to find the support for these communication security protocols, for these boot security protocols, for these runtime security protocols. However, there's this one piece, this last piece, that's more of a system level aspect, and that's really physical security. And as Chris and Ed have touched on, there are a lot of aspects of physical security that go way beyond what you can do from just a processor selection, and really get into the fundamentals of how do I protect the system and mitigate risks at the system. So let's go ahead and really, I guess, one of the key pieces that we want to look at in terms of the physical security is we've moved from a situation where our devices were primarily, I mean, they're non-smart devices. So devices have gotten smarter. And so we now have a lot more software, a lot more electronics in the hands of consumers or on business properties. And so the level of access that attackers have to products has greatly increased. I mean, previously, things might have been locked in a secure room with an armed guard. And so your level of physical security that you needed on your device was pretty low. But now some of those same types of devices that might have previously been in secured rooms or something like that are now migrating to the edge, where they're in people's homes or in businesses. And now attackers have access to those devices 24/7. And so that starts to need a higher level of physical security. So let's go ahead and dive into physical security a little bit more, and some of the attack vectors that might be available, might be present for attackers. So if we look at some of these physical attack vectors, one of the first things that you look at when you start talking about physical attacks is component removal. So basically, anyone with a good soldering iron and some good soldering skills can go and modify a printed circuit board as long as they have physical access to it. And you see there's a lot of literature out there about how to modify things like Xboxes and PS4s and stuff like that in order to be able to add additional features and things like that. So you're really you're being able to isolate and remove any of the integrated of any of the components that you have on your printed circuit board. That allows you to be able to have a very big attack vector into your system. There's also these things called cold boot attacks, in which they can actually freeze the contents of the DDR on your printed circuit board and start to read out the contents of memory. And so there's all sorts of amazing types of attacks that people have developed against electronics in order when you have physical access. So component removal is a big piece of physical attack vectors. Additionally, being able to access the pins of everything, like Chris mentioned, having access to the pins allows you to probe memory interfaces. So oscilloscopes have gotten really good and are really cheap. And so you can get a decent oscilloscope now and be able to see the contents of a DDR interface or an eMMC interface where you might have all of your code stored. So you have if these traces and these pins are available on your printed circuit board, then an attacker has the ability to go probe and access those. Similarly, you can look at oscillators. If an attacker has the ability to take an oscillator off the board and drive a clock in externally, then they can modify the time that the processor actually experiences, in which case they can elongate potential vulnerability holes or go through and try to trigger certain types of events by overclocking or doing anything modifying the time of that processor is going to experience. Additionally, you have power-related types of attacks where if you have access to the processor and PMIC interface, you're able to go and tell the PMIC to adjust the processor voltages. So you can overvoltage or undervoltage the processor in specific ways in order to be able to induce certain types of faulty behavior, in which case that can then start allowing you to gain access to different pieces of that hardware. So having access to that processor PMIC interface can be one avenue of attack. Additionally, there are differential power analysis attacks where by monitoring a particular power rail, you're able to understand what types of operations a processor is doing by the changes in voltage and or current on a particular power rail. So one of the kind of canonical differential power attacks is if you can isolate the difference in power when an encryptor is using a 1 versus a 0 in order to encrypt a bit, then you can start to gain information about that encryption key. And so there's a lot of work that goes into designing hardware encryption peripherals that basically make sure that the power used for one type of operation is the same as the power used for a different type of operation. So depending on whether the input is a 1 or a 0, the power utilized by the peripheral is the same. And so there's mitigations that go on there, but that's not necessarily true in all cases, especially when you're going to be using software to do parts of your encryption process or something like that. So having the ability to monitor those individual power rails is one avenue of attack. And then last, we get into tamper in and of itself, in which case you start physically going through and using lasers and probes in order to physically tamper with the individual devices. So how do we actually enhance our physical security to help reduce these risks? Well, system in package is the solution. So taking a quick step back, what is system in package? System in package really is that next step in heterogeneous integration. So basically with SIPs, we're integrating systems with silicon devices and not just increasing the number of things on a particular SoC or a particular silicon device. So basically, most devices that you get today have a single packaged silicon die within that package. With a system in package, you're looking at more of a system view of things. You're taking many silicon die, integrating them together. You're looking at passive components as well as discrete packaged components. You're integrating all of that onto a substrate as opposed to potentially just a single die in a standard discrete implementation, and then going through and packaging that together into a single IC. So what does an example of this look like on the next slide? So one system and package example. This one integrates a high-speed or a high-end processor, use a ARM Cortex-A processor. It integrates high-speed DDR memory. It integrates the power management, so you can see that there's an LDO and a PMIC die in the package as well as some non-volatile storage like an EEPROM in order to be able to have hardware revisions and potentially some information associated with the design there, as well as all the associated passives. And so really this takes what you would normally put on a printed circuit board and all of the exposure that those components have to potential attackers, and it integrates them into a single molded plastic device. And so that's really where we start seeing that SIP is going to enhance the physical security, because we're taking all these things and we're integrating them into a single package, as opposed to having all of these discrete accessible packages on a printed circuit board. So when we look at the SIP physical security, really because all of these components are within molded plastic, and really if we look at kind of what are some of the steps that that folks use today in order to mitigate some of these types of physical attacks, they use conformal coatings, which is basically encasing all of their components on a printed circuit board in some form of plastic. And so really SIP just kind of takes that to the next level, and now you get a integrated component and it's all encased in plastic. So that way it really becomes difficult to isolate or remove any of those integrated components. It also prevents memory interface probing, because really as though the integrated devices are connected together on the substrate, those pins or those signals no longer come out to the pins of the device. So now you have those connections completely within the system and package device. So you're able to have that level of security and increase the level of attack needed in order to try to get to that memory bus or that eMMC bus in order to be able to try to read out those contents. Additionally, some system and package devices can integrate oscillators, which can help prevent any type of oscillator or timing attack. That way, you basically gain more control over the oscillator that's integrated within the system. Now it is physically within the system and package device, and so now you don't have to worry so much about an attacker being able to change the processor's concept of time. Similarly, with system and package devices that integrate power management, that can help prevent some of those power attacks that we talked about. So you can have basically no or limited access to that processor and PMIC interface. So either that PMIC interface might be brought to some pins, but they're well within the BGA array and difficult to access, or they might not actually be brought out at all, and the processor can only talk to the PMIC through a dedicated interface on the system and package device. And additionally, with the integration of power management, you go from having a multitude of rails up to, 5 to 20 power rails for a system, and it becomes more of a single power type of input. So instead of being able to have access, for an attacker to have access and monitor any of the individual power rails for a particular processor or subsystem, now there's only a single power input, which kind of aggregates all of that together and adds quite a bit of noise when you're trying to look at things like differential power analysis. And so that can help mitigate some of those risks around certain types of power attacks. And finally, just like you have with things like trusted platform modules and other types of high security devices, SIPs can integrate some of those tamper protection and tamper detection type of features and integrate alongside any of the tamper response that the processor might support. So you do have the ability with system and package in order to be able to address a lot of these different types of physical security attack vectors and really mitigate the risks that you might face from a system perspective. So why Octavo SIPs? Well, with Octavo, we basically have work with a whole host of processor families. So we really have system and package devices built around a number of different offerings from Texas Instruments, ST Microelectronics, AMD, and from those that allows you to really choose the processor and the components that will meet the security requirements for your application. So whether you need certain particular hardware accelerators like true random number generators, encryption modules, hashing functions, whether you need certain types of secure key storage, whether you want secure boot with that hardware-based root of trust, or particular runtime security and resource isolation features, those are going to be processor specific. And with the SIPs offerings from Octavo, you're able to kind of pick and choose depending on what's offered by the particular processor family. So you have the flexibility to go choose the processor that's going to meet your security needs. And then on top of being able to choose that processor, the Octavo SIP is going to provide that enhanced physical security that we talked about, help you mitigate some of those physical attack vectors. Plus, there is a wealth of system design and security design expertise that has gone into developing the components and that is developing what has gone into the system and package device and developing the system and package device in and of itself. And then beyond the security aspects that a SIP can provide, SIP provides a lot of other benefits for designers in terms of reduced size, simplified hardware design, lower cost printed circuit boards and assembly, faster time to market, and a simplified supply chain. So there are a lot of benefits for system and package beyond just the security aspects that we kind of touched on here. And so now you're able to kind of look, and depending on what you do as part of that security development lifecycle, as part of that security mindset for your product, you want to consider, what am I doing from a hardware perspective? How can I utilize some of these hardware tools in order to make my journey easier? So with that, like I said, security is it's a secure development lifecycle. It's a mindset, and that is a very complicated journey that we all have to go through, and in order to design a secure product. And so in order to help along the way, you need software partners, you need hardware partners in order to make sure that you're using the right tools, that you're utilizing the right resources, so that you don't have to go through this alone. And so with that, Octavo has hardware offerings, Witekio has software offerings in order to pull you through that security process, so that way you're able to make sure that you have a product that meets your security requirements, and you can feel confident that you're able to bring that product to market with meeting those security goals and security needs.
Exactly, Eric.
And with that, I will open it back up to Ed and Chris if they have any last comments. And
I don't think I could literally, let me just finish this my train of thought before Ed and Chris jump in with their mass knowledge, I'm sure. Just to echo what Eric's just said, literally Witekio and Octavo together equals all your SIP needs, from security to development, etc., hardware and software together. On this slide, literally is just talking about our Linux long-term maintenance service, which is security, everything that Chris talked about with CVE scanning, vulnerability alerts, etc., in one nice package, as well as talking about the embedded kit, which is essentially Witekio. Thanks to our knowledge of doing this time and time again for over 20 years, we've created a product. So it's an IP that you can buy, you own it, and you can run your own vulnerability checks. Or if you'd like experts such as our lovely Ed and Chris, who you've fallen in love with, to do it themselves with you, then you can use our services. And if you're using Octavo SIP, we're partners. We've been partners for a while. We've worked together on projects. So if you get in touch, we'll always link together to do the best hardware and software combined, as Eric just said. So that is literally all this is saying. And with that, I'm going to ask if anyone has any questions. I can see one, but I think that Eric has already covered that, which was a question from Paul Ross asking, what type of security does SIP help with? But you've kind of gone over that. This was before you went into your lovely slides.
Yes,
So,
no, and if you have any additional questions, Paul, please go ahead and put them in the chat. If there's any aspects of the hardware and SIP in terms of enhancing some of the security aspects of your hardware that I wasn't able to cover, or you want some more detail on.
Yeah, exactly. If no one else answers, we're almost at time anyway, so it really doesn't matter in the sense of what will happen after this, so that everybody who's watching is aware. If you're watching on YouTube, I see you, hello, or if you're watching on LinkedIn, hi, and you haven't registered, doesn't matter. We're not after your data, but if you'd like to receive the slides, then if you register, I know who you are and I can send you the slides, because obviously there was a lot of information and our speakers sometimes covered the overview and not exactly what was on every single point. So if you'd like the slides, also the access to the recording and anything else like case studies or anything else you want to know about from Octavo or from Witekio's side, please do register. You can find it on our social media channels and on Octavo's social media channels, and that means you'll have access to all the beautiful content that we've made for this webinar, as well as our takeaways, etc., etc. So yeah, if no one has any questions, I'll just leave it. I can talk while I'll wait for you to type. If no one has any more questions, then all I have to do is to thank our amazing speakers. Thank you, Ed, thank you, Chris, and thank you, Eric, so much for joining me here and for telling us all about security on SIP, which was like, I thought it was going to be really scary, but you didn't go down the fearmonger route. You went out the this is how we're going to help you route, which I thought was very good. I liked that. So yes. Yeah, thank you very much, guys. Thank you. And thank you everyone for joining us and for watching us. So have a lovely evening and day, and I will see you all later. Bye-bye.
Thanks for watching. Cheers, everyone.